All right, welcome everybody. It's my great pleasure to introduce our next speaker, Michael Pinsker from Vienna. I was asked to say a few words about him. So I just say that Michael is a great guy, and he runs very fast, and he sings very well. And then I was really surprised to figure out that he's a great mathematician on top of that. So without further ado, I present you.
Thank you very much. So where are those pictures that you promised? Those old pictures. Okay, well, thank you very much, and welcome to this talk. So I'm just wondering who the audience is. Are there any students? Yeah? So, yeah, okay. So you're master's students, or?
Yeah, bachelor.
Oh, okay. And all the others are
Master's student.
master's student. Okay. Okay, so just to have an idea, and the rest are PhD or researchers. Yeah, so this talk is called Constraint Satisfaction Problems with Infinitely Many Values, but actually a large part of it will want to focus on infinitely values. This will be then the kind of second part. So what I'm going to do is really a gentle introduction to what we often call the algebraic approach to constraint satisfaction problems. So first I will say, the first part I will say what a constraint satisfaction problem is and how they can be modeled by relational structures. Then I will talk about this said algebraic approach in the second part. But the second part will be about finite structures. Then I will move to infinite structures in the third part. And in the end, I will talk a little bit about how we try to make infinite structures finite again to use the methods from the finite. Okay, so what is a constraint satisfaction problem, or what is an instance of the universal constraint satisfaction problem? It's the following: you are given variables and constraints on them. Yeah, I'm not saying what they are. But you can imagine constraints. So, your task is to give values to the variables such that all these mysterious constraints are satisfied. Okay, so that's your goal. We solve constraint satisfaction problems in our real life all the time. So, for example, when you solve a Sudoku, you're solving an instance of a constraint satisfaction problem, right? You have to assign values to the empty fields that are the variables, and their constraints, the rules of the Sudoku. Yeah. Or when you make a schedule for a conference, you organize a conference, you say you want to decide which speaker speaks when, and then there's somebody never wants to speak in the afternoon. There's some known people like this, and somebody never wants to talk right after that other person because the other person is doing a scrap and so on. So doing a schedule is solving an instance of constraint satisfaction problem, or solving equations, linear equations, or other equations. Yeah? Are typical examples. Okay, but usually we don't solve all possible constraint satisfaction problems. We don't consider all of them at the same time, but we focus on one particular kind of problem. Like, so I want to solve linear equations over the rational numbers, or I want to solve Sudokus, and so on. So I restrict myself to a certain kind of problem. And how do I do this? Or how can I model this? I fix a set of values in which the variables have to, where they have to go. Okay, and I fix a kind of allowed constraints, like the rules of a Sudoku, or the rules of scheduling, or the rules of equations. Yeah? Okay, so the kind of constraints that are allowed to come in. And how can I do this? Well, abstractly, a constraint then is just a relation on the set of values. Okay, and then like this, I get a relational structure by saying, okay, my relational structure has as a domain the possible values. And as relations, it has these constraining relations that are allowed to appear in an instance. Okay, and then the constraint satisfaction problem of that structure. Okay, where I restrict to this particular set of values, these particular kinds of constraints that I fixed, looks like this. I get variables, and I get a statement that says, well, this constraint has to hold for these variables, and this constraint has to hold for these variables, and so on. So they are all connected by AND. Okay, and the question is, do there exist values such that this is true in the structure? Yeah? So you could say such sentences of this form are called PP sentences. PP stands for primitive positive. And this means that they are existential quantification, and after that, just a conjunction of relations, relation of the atomic formulas. The question is this PP sentence true in the structure? So can I actually assign values to the variables such that all the constraints are actually satisfied? You know? Sometimes I also want to find the values, that's the search version of it, but well, in this talk, let's focus on the decision version. Is it actually satisfiable? Yes or no? Okay. And so the question in this line of research that we want to answer is, for which structures is this an easy problem? Once I fix the structure, is it an easy problem? And for which structures is it a hard problem? So what kinds of constraints are difficult to deal with, and what kinds of constraints are hard to deal with? Okay, and well, so here I say, okay, easy is polynomial time solvable in the number of variables. Okay, and hard is here displayed as well, NP hard. But this, in this generality, these CSPs, they also go beyond NP, or they're undecidable such problems. But a lot of this talk will be about P versus NP such problems. Okay, so let's look at some concrete examples. If the template, this fixed structure that defines the problem, is the integers with 4 relations. Okay, one relation is a unary relation that just says where the 0 is, and one says where the 1 is, and then there are ternary relations that allow you to express addition and multiplication. Then an instance of this problem is, well, as always, given variables, and then a PP sentence over this language. Okay, and the question is there a solution in the integers? Okay, and what is a PP sentence? It says, well, this variable is equal to 1, and this variable is equal to the sum of these two, and this variable is this times this other variable, and so on. So it's this huge conjunction, and in the end, what can you express? Well, you can express equations. Yeah? Equations using constants and multiplication and addition. So arbitrary equations. You wonder, is there a solution to the system of equations like that? Okay, and that's undecidable. That was Hilbert's 10th problem. Can you decide for a given equation if it has an integer solution? There's no algorithm doing this, since the 70s. Okay, so that's an undecidable CSP. But if as the set of values, instead of the integers, we take the finite field ZP, okay, then of course we can decide it, and we can try all the possible values. We can guess the values and verify in polynomial time if the given equations are actually satisfied by these values. So, and as it turns out, this is a complete problem. Okay. Now, what if we remove multiplication from the language? Then the CSP is just some linear equations, right? There's no multiplication anymore. And well, of course, I can solve this systems of linear equations. So this is then an easy problem. Okay, let's look at another example. If the template, so the relational structure that defines the problem is the order of the rational numbers, then an instance of the CSP of the structure looks as follows. We're given, as always, variables, and then these constraints which say this variable is smaller than this one, and this variable is smaller than this one, and. and I have to decide, is there a solution? Okay, when is there a solution, in your opinion? These constraints. Or when is there certainly no solution? If there's a cycle, there's certainly no solution. If there's no cycle, then there's a solution. I can certainly I can extend, and it's like a partial order. I can extend it to the linear order, and I can map it into the rational. Okay, so this is really the question: if this defines a directed graph on the variables, these constraints. It's really the question: does this directed graph on the variables have a cycle or not? Okay, and this I can decide in linear. Okay. So you see, even if the template is infinite, it can be an easy problem. Okay, and then this important example: if the template is the complete graph on 3 vertices, okay, so then an instance of the CSP looks how, when again given variables, and then the constraints say, okay, this variable has to be connected by an edge to this one, and this one, and that, and that. Okay, and that's really the question is, can I assign 0, 1, 2, value 0, 1, 2, such that all these constraints are satisfied? What does this really mean? Well, so this defines a graph on the variables, right? The constraints tell me which variables have to be connected. And then in the solution, 2 things that are connected have to be mapped to different values, right? Because the only edges that are in this template are the ones between different values. And there's no edge between a value and itself. So this means if this graph defined by the constraints on the variables is 3-carable. Okay, it's of course a NP complete problem. Okay, so you see there's really quite different kinds of problems that you can easily cook up with this notion as a CSP of a fixed structure. Notion of computational problem. Well, a famous theorem from not so long ago. Now it's almost 10 years soon, but it feels not so long ago to me. It says, probably means I'm getting old, but whatever. It says, Bulat and Juk proved independently that if the set of possible values is finite, then this problem is always in P or NP complete, so there's nothing in between. Okay. Yeah. Is this a great theorem in your opinion? Yeah, I see one person nodding, 2, 3. I'm not looking at the experts here. Is it a great theorem? Well, so this was answering a conjecture of Feder and Vardy that was 25 years old approximately at that time. So I mean, there were people working on this, and also we know that the proof is not easy of this. So it is a great problem. But on the other hand, if I just state it like this, it's okay. What does it say? It says these weird NP intermediate problems don't appear among finite domain CSPs. I mean, I don't know. It just means okay, these weird things are not there. What do you do with it? Yeah? It's not so useful actually. I mean, how would you then apply this fact? So I think just stated like this, if we rate it, so let's give it 8 out of 10.
You're not that old after all.
Sorry?
You're not that old because it is what youngsters do.
What?
Rate, I mean, rating is like more for youngsters than for old people.
Ah, okay. Yeah. Well, so whatever. But the theorem is in fact much better than that. It doesn't just tell us this abstract fact without any further information. It actually says, and one way of formulating it is that a finite template, if you want to know if the CSP it defines is in P, you just have to check if it has this algebraic invariant, whatever that means, I'm going to explain, satisfying this equation. Okay? So it's a very concrete separation of the NP-complete problems from the polynomial time solvable by one weird equation. I think this is really remarkable. Right? In particular, this lets you decide if you give me some finite structure, I can tell you if it's an incomplete problem or NP. Okay, so with this, it's 10 out. Okay, so what is the strange algebraic inversion that tells me that makes the problems easier? Apparently, it's called a polymorphism. Okay, so let me abstractly define what a polymorphism is. If you have a relational structure, then a polymorphism of this relational structure is a function on this structure in L variables, okay, finitely many variables, that is a homomorphism from the Lth power of the structure to the structure itself. Okay, what kind of how is the power defined? Well, you can also write it like this. It has the property that whenever you plug into its arguments tuples in a relation of the structure, and you apply this row-wise, the function, then the resulting tuple is again going to be in the relation. So it's really like a higher dimensional homomorphism from A to itself. Okay, so it's called a polymorphism. And the set, if you collect the set of all polymorphisms of a relational structure, then we denote this by pol of A. And this pol of A, well, it has two obvious properties. First of all, it always contains the projection functions. Yeah, of course, if you apply a projection function to tuples in a relation, say it's the first projection, yeah, then the result is the first tuple. It's going to be in the relation. Yeah. And then it's easy to see that it's composition closed. So if you have such polymorphism and you plug in other polymorphisms, you again get a polymorphism. Okay. So this set of polymorphisms, you could view them as the set of term functions of an algebra on the domain of the structure. Okay. Because well, what are term functions? How do you build term functions? And you first say, okay, projections are term functions, and then some basic operations are term functions, and then everything you can compose, you close. And this is exactly this kind of thing. So these polymorphism objects, they are exactly the sets of term functions of algebras in the domain of structure. And basically this here says, well, this algebraic invariant, it means a polymorphism. So the CSP is in P only if there's a polymorphism that has a 6 area and satisfies these equations. This equation for all x1. Okay, let's look at some examples of polymorphisms. Well, we had the template Q, the rational numbers with the order. That was the CSP of this was a digraph acyclicity, right? We found out that basically it amounted to solving an instance, amounted to deciding whether a finite digraph is a cycle. And indeed, this structure, it has a polymorphism, the minimum function. Yes. It preserves the relation of that structure in this way. And this minimum function here, at least there's some non-trivial thing. Yeah? So it doesn't, we don't see immediately how this solves your CSP, but there's something there. Okay. Also, the CSP over the field, P element field with, not field, just addition. Okay, ZP with a plus and 0 and 1 constants. This has this polymorphism. Okay, why? Well, everything that you can. So you could just. well, you can just check it on these relations that it's preserved by this function, ternary function x minus y plus c. But the moral reason is that solutions, what are solutions to this to an instance of this CSP? They are affine spaces. Yeah? So because the solution sets, we said the CSP of this is solving linear equations. Okay, so solution sets are affine spaces, and affine spaces are closed under x minus y plus c. So there's this non-trivial polymorphism. Now, we also saw the CSP of K3, the three-element complete graph, and we said, well, this is basically the three-coloring problem, NP-hard problem. Do you see any interesting polymorphism of this? No. So any function on from this. Three-variable function set preserves this structure. So they're the projections, right? Okay, give me a unary function. Give me a unary function that preserves one variable function that preserves this and is not the identity. So just a function from K3 to itself that does something that preserves the edges. Well, what can you do with K3? Yeah, I see some hand movements that are the correct ones. Yeah, you can turn it around, right? I mean, so it has some non-trivial automorphism, right? Automorphisms are unary, particular unary polymorphisms. And so these are polymorphisms. But if you ask about the third power, there's nothing. There's really nothing. They're the projections and composition of automorphisms with projections. Okay, so those are basically all, just the automorphisms. So you see there's some unary polymorphisms, but nothing higher area. Okay, and that's the reason why this is a hard problem, really. So we have the following basis. This baby theorem is really the basis of this algebraic approach to CSP that I mentioned. If you have two structures, A and B, on the same domain, and B has more polymorphisms than A, okay? So every polymorphism of A is also one of B. Then APP defines B. Okay, so that means every relation of B can be defined in A by a primitive positive formula, so just using existential quantification and conjunction. Okay, and this then easily implies that the CSP of A is at least, I wrote hard, at least as hard as the CSP of B. Okay, well, CSP of B reduces to the one of A. So what's the reason for this? For this second implication. I mean, if you get now an instance of, I want to reduce CSP-B to CSP of A, okay? I get an instance of CSP of B, okay? So that is a P formula that says there exists x1, exists x2, and then relation of between the two variables and so on, okay? But now I know that every such relation, these are relations of B. I know every such relation is PP definable in A. Okay, so I can replace this by the PP definition in A. Okay, yeah.
Don't you have to compute it also to replace it?
Well, these I want to give you a reduction, right? So I get the instance. And B, I know before A and B, right? So I can fix these formulas before. I don't have to do this on the spot. Okay, and then now I replace every relation here by this PP formula over A, and now suddenly it's a PP formula over A. Okay, and now I ask CSP of A, does it have a solution or not? Okay, so it really easily then reduces. Okay, and the fact that the first implication, that if the polymorphisms of A are contained in those of B, then A PP defines B, is not very hard to show, and it's actually rather old. But it's, you don't see it now. If you don't know it already. But it's not very, very hard. Okay, so this is the basis. It tells us the more polymorphisms, the easier the problem. Yeah? So it's the moral outcome of this. Okay, so how great is this theorem? I'm not going to do a rating again, but is it when is it useful? Well, it's only useful if I want to compare structures on the same domain. It doesn't say if A lives on a 2-element set and B lives on a 5-element set. This doesn't happen. Right? But okay, it's already good for this. And indeed, with this one can actually classify the complexity of all CSPs whose template has a Boolean domain. Okay, so this includes SAT problems, Horn SAT, whatever. Okay, but as I said, its limitation is that I cannot deal with different finite domains. And to prove something like this Bulatov-Shuk great theorem, you have to get a machinery that allows you to look at all finite structures. Okay, and to do this, you can see going from the structure A to pol of A as some abstraction from A. And now we do one further abstraction step. And this is the following step. We saw that the order of the rationals has this minimum function. Okay, and now I don't want to actually care about the concrete minimum function. I can observe that it has a function that is commutative. The minimum function is commutative. Okay, so this sentence here, this sentence is true for the polymorphisms of the rationals. There is a polymorphism. There is a function, a binary function that's commutative. And that fact is a non-trivial fact. Yeah? For example, K3, it has nothing higher array, so it doesn't have this. Yeah? Or the abstraction from this one, I said, well, this template that defines linear equations over CP, it is invariant under this ternary function x minus v plus y plus c. But I can abstract from this. I can say, okay, it has a function that satisfies these equations. Okay? Because this function x minus y plus c, it does satisfy this. And if you insert x, y, then these cancel out and the result will be y. And the same if I insert y, x, x is going to cancel out and y is going to remain, and therefore these three equations are true for this ternary function. Okay. And okay, so I mean, of course, you cannot judge now if this is an interesting equation, but I tell you it is. Yeah, so, this also, it's an interesting equation. What can we say about K3 that we know is a hard problem? Well, you could say, well, there is a unary function that satisfies f to the third of x equals x, yeah, to shift this automorphism. But this statement, there exists a unary function such that it's not an interesting statement because it's also true for the identity function. Right? So this abstract statement is a trivial statement. And in fact, you cannot, in the polymorphisms of K3, find any interesting such equational statement that is true. Okay, there's none, and that's the reason for its hardness. Okay, and here these are non-trivial. That's the reason for the polynomial tensor. Roughly, the first one is a bit doubtful. Okay. Okay, and now what I said on these examples, I'm just now going to say it in general. An equational condition, or also called strong Maltsev condition, is a sentence that asserts the existence of functions satisfying a number of equations. Okay, so they exist f1, f2. These are function symbols, such that for all variables, and then this term over these functions equals this term over this function. Okay, that's a strong Maltsev condition. A strong Maltsev condition is called trivial. I already used this word several times. If it is true in any polymorphisms of any structure, so it doesn't tell me anything about the structure. And you could alternatively say it's trivial if it's satisfiable just by projection functions. So satisfiable, it means I can assign projection functions on a, say, two-element set, doesn't matter, to these function symbols, such that all these things become true. Okay, that's a trivial condition. Okay, and this one here, for K3, this is a trivial condition. This one is not a trivial condition. Why? Can this be true by a projection? No. F of xy, f of yx, if f is the first projection, then we get x equals y. But it's not true. Yeah? Can this be a projection? Well, if it was the first projection f, then we would have x equals y. No, it was the second, x equals y. Third, here we see x equals y. So in this sense, these are non-trivial. Okay, so we see some templates of CSP satisfy non-trivial conditions, others don't. And this gives now was the motivation necessary definition for a better theorem than the first one. It says before we compared polymorphism clones, sets of polymorphisms of structures on the same set. Now I don't require this. I just require A and B to be structures on arbitrary finite sets. Okay, and this adolescent theorem, it says, well, if every equation that is satisfied by A is satisfied also by polymorphisms of B, then APP interprets B. So before we had PP defines, yeah? Now interprets is a generalization of this. So it's somehow allows you, defines, they have to live on the same set for this even to make sense formally. Interpret, it allows you to change set. So I can also say, I don't want to define it formally, but it says that you can obtain B as by first taking a power of A, finite power, then going to a substructure of A that you can define, and then factoring it. Okay, and the result should be B. That means A PP interprets. Okay, and again, but this is similar as before, just a little bit more technical to write up, but not hard. If this is the case, A PP interprets B, then the CSP of B reduces to the CSP of A. Okay, so that's not hard. It's just replaced by variables, then by tuples. Okay, so now we have a tool to compare arbitrary finite structures. I didn't write finite here, but it's an assumption that is there in this whole chapter. That can be improved a little bit further. Okay, in fact, we looked at equations where I could say f of g of h variables equals, I could build terms, okay? And as it turns out, this is not necessary, yeah? So I can just look at equations where there's one function symbol like commutativity, f of xy equals f of yx. No nesting of functions. And this is also sufficient for a regression. So if the non-nested equations that are true for the polymorphisms of A are contained in the non-nested equational conditions that are true for the polymorphisms of B, then the CSP of B reduces to the CSP of A via a construction. It's called PP construction rather than PP interpretation. But we don't need to know here what exactly this is. Okay. Well, so what can we tell from this? say you have a finite structure, okay, and you somehow see that it satisfies no non-trivial equations. It's polymorphisms, so it doesn't have a commutative function, it doesn't have this other function, this ternary interesting equation. Say you can somehow see this. And you might be able to do this, right? For example, this K3, I mean, a student can figure out that it has no polymorphisms. Yeah, you do a little bit of, combinatorial reasoning, and then you figure out, okay, there's really nothing in there. What does this mean? Well, it means there's nothing in this. Yeah. So in particular, this is going to be contained in the equations of any other structure, okay? Because there's nothing. This means your structure, of which you saw it has no equations, will PP construct everything I wrote here. Everything means every other finite structure, okay? So this means your CSP is as hard as possible among finite structures, yeah? So in particular, CSP of finite structures is always an NP because we can always guess the values, verify. And you know there are some NP complete ones, so you will know your CSP is NP complete. Okay. Say you don't know three coloring is NP complete, yeah, then you could prove it this way. Say you know you don't know three coloring is NP complete, but you know that SAT is NP complete, and this would now be a proof without, I don't know, whatever proof you learned, whatever induction you learned in the TCS book. Okay, so this puts us in the situation that, well, whenever we know this, we know the complexity of the CSP. So naturally, what do we have to ask? We have to ask what happens if the negation holds. So if this is non-trivial, can we say anything? And in fact, so this is the cool thing about this field, just from assuming that you have a finite structure satisfying some non-trivial equation, non-nested, you can derive like incredibly many things. Yeah. So, and I put some of these. So you just know it's non-trivial. Then you know you have a six-array function satisfying this equation. Okay. So, and is this one non-trivial? Yeah, it is. Okay. Because you see, there's never two variables in the same position in this equation. So this cannot be a projection. If this was a projection, I would get x equals y or y equals x. Or something. So this is a non-trivial condition. And anything that satisfies anything non-trivial satisfies also this one. Okay, it's called a six-array Siggers equation. And then you also get this one, yeah, f of a four-array one that satisfies this area rare equation. It's called a four-array Siggers condition. And you also get a polymorphism that actually polymorphisms of all prime arities you get in your domain, satisfying this cyclic equation. Yeah, so it's invariant under cyclic shifts of its variables. It also can't be a projection. Yeah, if it was a projection, I would get x1 equals x2 or x2 x1 x3 or something like this. Yeah, this was actually proven by a member of the audience here. Actually, the earliest such statement was this one. It's called a weak in U equation. So whenever you plug in x to all but one variable, then you can shift around this one other variable where you want the result won't change. Weak in U. So you always have all these things happening, just assuming non-triviality and finiteness. Okay. And as I already said before, these things imply that it's in polynomial time. This is not, so if you know this, from this to P it's a big thing. Yeah. Okay. Going infinite. So what did we see? What examples of finite domain CSPs? We saw, well, so actually I didn't give it as an example, but SAT is obviously on a Boolean domain. Boolean domain. We saw 3 coloring by looking at Kn instead of K3. You get NK coloring. Linear equations, nonlinear equations. Those are finite domain over CP, or finite fields in general. Those are finite domain CSPs, the typical ones. And yeah, I don't know how many others there are variants of SAT, but then it's actually not, I don't know, there are not so many natural examples anymore. Computational problems that appear as finite domain CSPs. But if you allow your template to be infinite, you get a lot of more interesting problems. So I already mentioned this one here, solving equations over C, that's undecidable. Solving equations over Q, yeah. Or just linear things over C with order restrictions, additional ones, the natural problems that are of numeric flavor. Okay, these are great problems here because they are obviously very natural. The bad thing about them is that we can't say too much about them because they are hard. The algebraic approach that I presented doesn't work in a uniform way, at least. And so yeah, nice problems, but I can't say much about them. So we're going to focus on a different kind of combinatorial problem that appears among infinite domain CSPs. We already had Q with the order that models that digraph acyclicity. So digraph acyclicity is obviously like a nice problem, and you cannot model it as a CSP of a finite structure. So you really need this here. Then over Q, you could also look at the betweenness problem. That's actually one of the first NP complete problems from the 70s. So this problem is you're given variables and you mark some triples. And the question is, can you order the variables linearly in such a way that whenever a triple is marked, the middle thing of the triple becomes the middle with respect to that order. And so that's a complete problem. And this you can model it as the CSP of Q with the ternary betweenness relation. It's easy to see that it's exactly that problem. Then, yeah, unbounded scheduling. What do I mean by this? You might do a schedule in such a way that you have a fixed number of slots and you want to distribute your people for the conference among this fixed number. But often it doesn't work that way, right? I mean, the number of slots you will have might depend on the number of people who are even interested in giving a talk. So whenever your set of values is somehow not fixed, then you're going to end up with an infinite. Then there's a nice class of coloring problems. So the problem given given a graph, okay, undirected graph. Your task is to color the vertices with 2 colors, red and blue, such that you don't get a monochromatic triangle. So that's a nice problem. You can model this as a. So formally, I mean, you're distributing 2 colors for your vertices, but still to model the problem as a fixed template CSP, you're going to need an infinite structure. Or coloring, you're given a graph, the problem where you're given a graph and you have to color edges with 2 colors, red and blue, and your task is to avoid monochromatic triangles. So nice. And problems of this kind, they usually require an infinite structure. Okay, infinite fixed structure. Then also what I find nice is these graph orientations. So you're given an undirected graph, okay, and you don't like some, say you don't like some directed graphs, like a directed cycle, okay, and your task is to orient the edges of the undirected graph in such a way that you avoid these things that you don't like, this fixed set. So this recycle. These you can model, you can cook up infinite structures modeling these problems. Yeah, so this first class, I would always call them, or for me, they're always of the kind forbidden pattern problems. Yeah? So even the CSP for betweenness, the betweenness problem. Okay, so you fix a signature, say like an order symbol. Okay, and this betweenness relation, it lives over the rational numbers. Okay, and you know this order relation, it doesn't have loops, and it doesn't have an undirected edge, and so on. Okay, so there are a few forbidden patterns, and now you are supposed to distribute among the variables this order relation in such a way that all the constraints are satisfied. So the constraints are going to tell you, well, this always has to be true when the triple is marked. And moreover, you're not allowed to distribute this order symbol in such a way that none of these should appear when you distribute the order symbol. Okay. And well, often for these forbidden pattern problems, you can actually come up with an infinite structure whose CSP is exactly that problem. Okay. And this infinite structure that you get, you want, I mean, it is then, or the kind of structure that you want is the following, okay? Or in other words, what's the difference between these structures here and the CSPs here? These nice ones, where we can actually do some work, have, first of all, the following property. If you look at their automorphism group, okay, and you look how it acts on n tuples, okay, then there are just finitely many of different n tuples. Yeah, so it acts with finitely many orbits. Things in the same orbit have exactly the same properties. So what does this tell you? This tells you that if you have an instance with 1,000 variables, then up to this action of the automorphism group, there's only finitely many possible solutions. Yeah. So although the structure is infinite, every single instance there's just finitely many options. One of these orbits. Okay, but that's not enough. So such structures are called omega categorical. But that's not enough. We moreover want a bound such that we can tell what the orbits are. Okay, so this is called homogeneity and boundedness. And what does this really say? It says, well, let's maybe look at an example at Q. What are the orbits of the automorphism group of Q? What are the orbits if I let this act on tuples? Yeah, on Q to the, what is it here, K or N? Okay, so if N equals 1, how many orbits are there? So if I see a 1. Okay, very good. if I can send any rational number by an automorphism to any other rational number just by a shift. Yeah. Okay, so that's just one orbit. And then n equals 2. How many orbits of pairs are there? Which pairs can I send by an automorphism to which other pairs? Well, can I send this one to this one?
The lower one is not in Q.
Over Q. I don't know. It's very good. Listen. Can I send the first to the second? Sure. Yeah. Why not? It just has to be monotone. You can do a piecewise linear function. So there are three, yeah. So what are the three orbits? The first one is smaller than the second. They are equal, or the first is bigger than the second. Okay, so they're just three orbits. And now you start to see the pattern, right? How many triples are there? Well, it just depends on what the order relation says on this triple, right? There's just finitely many possibilities. Okay, and this is what is called this homogeneity. It means that if I have a long tuple and I want to know what its orbit is, I just have to look at the suborbits of size d. In this case, suborbits of size 2. Yeah? If I want to know for a long tuple of rational numbers, what is its orbit? I just have to look at pairs and how they are, what's their relative position. Yeah. So that's homogeneity. And then this boundedness, it means, well, say I write a fake tuple, like I just did with pi. No. I say, okay, let's look at this tuple where the first one is smaller than the second, and the third one is second is smaller than the third, and the third is smaller than the first, and okay, whatever. If I say, let's look at this orbit, then you're going to tell me, well, no, this doesn't exist, this orbit, because this would mean that x1 is smaller than x1. Okay, and this is this boundedness. It says, just by looking at locally, I can see which are actually valid orbits. Okay. Yeah. So I have an efficient way of telling what orbit actually is there. Okay. Now, yeah, and these are the conditions under which we can somehow work reasonably, like in the finite, just harder. But in principle, the same approach applies. Okay. Okay, and in fact, we have a hardness criterion as in the finite. What was the hardness criterion in the finite? It was, well, if there are no equations that are satisfied, then we know immediately the problem is hard. And we have the same thing here with a slight change. If the local equations are trivial, then PPA, our template, constructs everything. That means every finite structure, even if A is infinite. Okay, omega category infinite. And this implies that the CSP is NP hard. It can be outside NP, but it is at least NP hard. Okay, and what does this local mean? It means if I look at these polymorphisms restricted to a finite set, okay, then these restrictions, they satisfy no non-trivial, non-nested equation. Since the equation is non-nested, I don't have to care if they lead out of, if their values go outside of this finite set. So as soon as, if I look at the polymorphisms, I look at their behavior on finite sets. As soon as there is somewhere a finite set where then we call this naked, yeah, where there's nothing going on, we know the problem is NP. And yeah, so this is the infinite version of this hardness criterion. It's not very difficult to show. Yeah, this is just like somehow the basic machinery. So again, as in the finite, we have to ask, okay, what happens if the negation of this holds? Yeah? What if it's not naked anywhere? Yeah, then what can we say? And if you remember, in the finite, then we had these algebraic consequences. Yeah? Suddenly there were all these equations popping up. And here we also have an equation popping up. Yeah? So indeed, if you have an omega categorical structure. Okay, so it's this rich automorphism group, and we know that it's the equations, non-nested equations of its polymorphisms are non-trivial everywhere in every finite set. Then we know there is a six-area polymorphism and unary polymorphisms UV, such that this equation is true for all x, y's. Okay. We also had this in the finite, this equation, just without the u and the v. Okay, but the u and the v, we don't care so much about this because, again, if f was a projection, then this would say u of x equals v of y for all x, y. It's impossible. So obviously this is a non-trivial condition. Okay, and in fact this is not so. Yeah, actually we showed this in 2016 or so. We were Bartel, and for a long time this was the only known consequence from non-triviality. In the finite we had all this rich class of equations popping up, and there we had really only this one, and this was a bit depressing. But a few years ago we got many more, but the state of the art is we still want many more. That's one of the reasons why we're here. So we still know much less than in the finite. And we also don't have an algorithm that this would give to us. Okay, in the finite, this then gives us an algorithm, and we're done with the complexity classification. Okay, so what is the trouble in this situation, in the infinite situation? So okay, we assume that the problem is not obviously hard. We get this algebraic consequence, and now we want to use this to design an algorithm. Say we want to do this. We want to prove, okay, if we have this, then it's in P. The problem is, what is this f? I mean, we really just get the existence of such an f, but this f, it's a function from an infinite set, or the sixth power of the infinite set to the infinite set. So it's just a real number. I mean, thinking set theoretically. So in this generality, it cannot be useful if we only know that about f, that it satisfies this. It might not be even a thing that we can compute, or it cannot be useful in this generality for algorithms. So that's what I mean by f might be ugly. So what we want is we want somehow f to be an f that we can work with, that we can even represent to an algorithm. Because the f we can, I mean, the problem is defined, the CSP of A is defined by the structure A, okay? And if we know this A has a nice polymorphism, we can fix this beforehand, before we get the instance to use it in an algorithm. But there must be a nice F for this. Okay. And what we want really is, you see these infinite domain CSPs, they are somehow about, we want to look at the structure modular the orbits of this automorphism group. Yeah, I mean, our assumption on the infinite structure is that, okay, it's infinite, but if we look at the triples, well, there's really just 3 different kinds of triples. Yeah, and if we look at the quadruples, there's really just 4, just finitely many such quadruples up to automorphisms. Okay, so in that sense, we want to make it finite, and we don't want to actually assign values to an instance. So if I'm given an instance to CSP of Q, I'm given an instance, so x1 smaller x2, or let's say between this. Okay, so we look at this CSP, and I get an instance, so I get variables, and some triples are marked. okay? And I have to, my task is to assign rational values to these variables so that whenever a triple is marked, the middle thing of the triple becomes the middle thing with respect to the order. So formally, I have to assign rational values, but what I really have to decide is which one is smaller than which one and of these variables. I don't care about the actual values. Is this 1/3 or minus 1/5? Yeah. So what I really have to decide on is an orbit. Yeah? And the problem is, I now know there's this polymorphism satisfying this equation, but it doesn't act on orbits. Yeah? It's not compatible with the dividing of the structure into orbits. Yeah? And that's why we can't really use it in this reasoning. Okay, and that leads to the following definition. If you have a structure, forget about the homogeneous assumptions we work under it now all the time. We're not going into detail anyway. A function on a structure is called canonical with respect to the structure if it acts on the orbit. So if it preserves the equivalence relation that is given by the action of the automorphism group. And such a canonical function, I can actually use it in an algorithm. So, for example, the function on Q that sends x to minus x is canonical. Okay, why? If I have two triples, or two tuples, okay, I have two tuples, and they belong to the same orbit. Okay, so what does it mean they belong to the same orbit? That means they might have different values of rational numbers, but they are ordered in the same way. Now I apply minus x, the minus to them, then they just get flipped, but they then still belong to the same orbit afterwards. The orbit changes, but it changes the same way. So that's a canonical function. Okay. The minimum function is not canonical. Yeah, so we saw before, okay, the rational numbers with order has this great polymorphism, minimum function is commutative, but it's not canonical. Why? Well, it's written there. If you have two pairs, A, B, and C, D, and you know that A is bigger than C, and B is smaller than D, and you apply the minimum function, if it acted on orbits, then from this knowledge and this knowledge, I would have to know how the relation is between those two. But I can't tell, right? I can put values so that the U becomes smaller than V and the other way around. So that's not a canonical function. So although this minimum function it's commutative and it is actually turns out to be useful, but it's not. I cannot really use it in a very obvious way in my algorithm to solve the CSP of Q. Okay, and in fact, this is a statement that says, well, if you have a canonical function that satisfies this equation that we know we always get, then the CSP is really impede, and I can really use this, like in the finite. Okay. So the problem really is that we know always if the CSP in the infinite is not obviously hard, then there is an equation. If the equation is even satisfied by a canonical thing, we know it's in P. The problem is we don't know that we get this canonical. Okay, and there is a.
What is the role of this U and V? Is it some just artifact of the proof, or is it?
It's necessary. Yeah. So I don't know how to. So the statement is false without the U and V. I don't know how to. Well.
Like the previous statement, not this statement.
Yeah.
The one that you can get.
Yeah. That you can get this. So it would be false. Yeah. So this one, right? It would be false if you remove the U and V. it's not so easy to explain. So okay, I can give you an example. So you could have
But my question is different. Do you need to assume anything about U and V? Because you said that F is canonical, but how about U and V?
U and V is going to be elementary embeddings of this, so it's going to be canonical. Yeah. So these are not the trouble. The trouble is the yeah. Yeah, it's necessary, and it comes somehow from the fact that when we prove this, we still look at the structure modulo orbits. Okay, when we prove this statement, and so this is before the definition of canonical. We still look at the structure somehow modulo orbit. We do some kind of finite-ish reasoning, and then we lift the result of this reasoning to actual functions on the infinite structure, and this from this going away from the thinking modulo orbits, you get these they are not automorphisms, but you could think that they are automorphisms. Morally, they are elementary embeddings. It's very high level now. But I think I have no chance to get into deeper reasoning. Okay, so we conclude that we somehow need canonical polymorphisms, and well, there's just two things that that I want to say about this, but without going into detail. So first of all, these canonical polymorphisms in general are not rare, and that's a consequence of Ramsey theory, or Ramsey's theorem in the simplest case. Yeah, so canonical means that you have this function on this infinite structure, and you have this equivalence relation given by the automorphism group, and then somehow you want it to behave regularly with respect to this equivalence relation. And it's Ramsey's theorem that gives you then a new function that also behaves regularly. So they are not rare, and yeah, we have somehow methods of producing them, but not always. Yeah, so. Okay, all this can be used to show complexity dichotomies also for many infinite structures. And this is kind of random list, but listing a lot of the results that were shown in the last 15 years. If A is any structure that is definable in Q, so Q itself with the order, or Q with the betweenness relation, or Q with whatever relation you make up, invent over the order. Or it's definable in the random graph, so it's a kind of graph structure, or it comes from a graph, any homogeneous graph, tournament, partial order, whatever. If it's any such template, then if it has this the polymorphism satisfies this equation, then the problem is NP, and otherwise the CSP is NP complete. This is a lot of research that's being collected over many years, and we somehow hope this always happens. And in fact, the conjecture is whenever you have a structure that is definable in such a debounded, dehomogeneous structure, like a structure where you have just finitely many orbits of tuples for every arity. The orbits, you can tell what they are by looking at small suborbits. Whenever you have such a structure, then we hope that the problem is either NP complete or NP, and P is exactly characterized by the satisfaction of this equation. Okay, but I think we are far from this. Thank you very much.